actually going to direct us in the way that we need to go here today. Y'all have seen that before, right? That's the one we did last time. We did like 4 different questions from it. Yeah? Okay. So what is it that we do with region R to create a solid whose volume we can measure? What do we do with it? We rotate it around some axis, right? Maybe it's the x-axis, maybe it's the y-axis, maybe it's some other line, whatever, right? So we take that, we rotate it around some axis, and that rotation helps us visualize the volume, right? The shape of the solid, we find the volume. You guys are doing really well with that. Does that make sense? So let me ask you a different question. What if I told you that there was a way to take a region like that? Gotta put your thinking caps on here. What if I told you there was a way to take a region like that, like R, and not use rotation of any kind, use a different mechanism entirely and create a solid, like a 3-dimensional solid shape? Yes. Can you imagine or think what we could do to achieve that? No rotation allowed. What could we do with that and still create like a solid shape whose volume we could measure?
Bring it towards us.
Bring it towards you.
Or away.
Okay, so like almost just like straight at, so not a rotation, but just like straight at you. Interesting. Can you guys picture what he's saying? So almost, I hope I don't mess this up. I'll do my best. So check this out. What if I drew the x and the y-axis like this? What I'm trying to do here is do a perspective drawing. So here's the y, here's the x. Can you see how I'm trying to make it look like the y is like going back into the wall? It's like going, out there somewhere. Does that make sense? So if I was going to do that, then region R would kind of look like there's the line, and there's the curvy part. Something like that. I know it's not quite perfectly to scale, but can you see it? So if region R was going to come straight out at Jake or straight out at you, would you guys agree with me that the resulting solid would kind of look like this? I'll do this in a little bit of a different color. Does that make sense? Can you see it? Can you see that solid? You see how it's almost like the way that I like to and this is far from like a rigorous mathematical term, but I almost like to think of the region as like something's like growing out of the region straight up. So like the region is like a farmer's field, and like something is growing straight up out of it, creating this solid. And we could find the volume, we could find the surface, or we could find all kinds of things, but we would focus on volume if we were going to do that. So Jake, your idea is really good. And I think this is where I would go with this. Like what he said, what if R just sort of grew right out at you? There's no rotation involved, but it is a solid, right? It is a solid. And so that's what we're going to be doing. So let me illustrate this a little bit further. I got some computer stuff. We'll do some Play-Doh, and we'll do some examples. And hopefully we'll get done with most of them. If not, we'll do the last couple on Tuesday of next week. If I were going to show how this is represented, it's not going to be, again, a rotation. It's going to be an accumulation of stuff like growing up out. And I want to talk out of the region. I want to talk about what the stuff is. Check this out. I could illustrate the stuff growing out of the region by doing something like this. What does that look like to you? A rectangle, maybe a square, something like that? So what we would say with this is we would say that this region that Jake kind of started describing to us, we would say it's created not by accumulating rotation, like accumulating disks or washers like we did before. We would say that we are accumulating what we call cross sections. Cross section. So we would call this green rectangle a cross section. The way that I like to think about it is this. We'll do this with the Play-Doh for sure. I use this. I use the shape that I did. Like, can you imagine if my three-dimensional shape over there was a block of cheese, maybe? Anybody else here like cheese? Like, if I could somehow survive on just cheese, I'd be very happy. I don't know if you guys like cheese too, but I do.
Like Tillamook cheddar.
Oh, perfect. The big block of Tillamook cheddar. Yeah, for sure.
Medium.
Yeah, it's great. Can't beat it. I don't think. I don't think it's all that. I don't think it's as healthy as a salad, but it's really good, right? Put it on your salad. Anyhow, can you see that if you took a knife or something and you cut straight down on this block of cheese, and you open it up, you'd have these rectangular faces facing you, wouldn't you? Like that little green rectangle. That'd be like someone cut straight down through parallel to the y-axis. That would be an example of a cross section. You could cut a cross section. We'll do that with your Play-Doh, and we'll see just how good you are at, or I am, because I like to challenge myself too to be able to make those little sculptures out of Play-Doh too. Okay, so I wanted to like piggyback off that and say, just make it clear that we have done volumes created by rotation, and we'll continue to do that in the future, but our final topic is, how could you create a solid without using rotation? That's how. That's how. Okay. So I thought I would also show you some little computer animations here to help you visualize this, and we'll get to the Play-Doh. So let's see here. You can all see this, right? Hey guys, check this out, please. So this is an example of what we're talking about. Can you see how the y-axis and the x-axis are drawn in a perspective drawing? The y-axis is kind of going away from us, and the x-axis kind of going across. Okay. And you can see here, maybe you can see that the cross sections are defined as equilateral triangles, and you can see that represented there. You can see there's other options. You can see the two functions. One of them is a parabola. The other one is a trig function, a sine curve. And you can see down below at the very bottom, do you see how it says n equals 1? What do you think that n equals 1 means? Say one more time.
One solid, like one rectangle.
There's one, I think if we combine which of the two you said, there's one cross section, right? So this is giving a really terrible visual on what this looks like. So what I need to do is I need to increase the number of cross sections. And as I increase the number of cross sections, what will happen to the cross sections? Get skinnier and skinnier and skinnier. And so if I increased it from one cross section to 4 to 33 to 34, you can start to see this shape is, the shape is developing pretty nicely. There's still the base region. That's what these are growing up out of. But there's what it actually looks like. What would you say that is? Mountains? Kind of cool. How about more cross sections? What did you guys say it was? The thing, oh yeah, the Opera House thing, yeah. So there's 36, 37, 38. You can see that the more rectangles you do, the better it gets as far as becoming a smoother and smoother curve. And so again, you see how there's no rotation. It's not like a region, as you saw those other animations and you tried to make with your Play-Doh, there's no region getting swept around an axis. These triangles are just going straight up out of this region. We could change it to other things. How about squares? Take a minute and think. There's your base region. Can you picture in your mind what this would look like with, instead of equilateral triangle cross sections, how about squares? Can you picture it? See if you pictured it right. I'll switch it over to squares. So there's your base region still. It's growing up out of that. And now all your cross sections are squares. I'll switch it. Equilateral triangles, squares. Does that make sense? Did somebody just say no? Or is that good? Okay. I just want to make sure that we're doing okay. Regular pentagons. Interesting, right? See what that looks like. Oops. Question?
Yeah, so when would we in math want to use a shape like this? Like how, when?
Anytime you need to program a computer, you need to be able to quantify a shape using math, whether it be volume, surface area, height, width, length. That's what we're doing. We're trying to take crazy shapes. Like when would somebody use this? I don't know. Like use this particular pentagonal shape. I don't know. Maybe it needs to be hexagons. Maybe it needs to be semicircles. Or, see the semicircles? Or maybe the base region needs to be something else entirely. Like what we're really talking about here is kind of the, and this is not, certainly not the programming language that they use, but we're talking about the basis for like 3D printing, aren't we? Taking cross sections and laying them on top of each other in various positions and shapes and thicknesses and creating something, right? So being able to quantify it, being able to use math to describe something physical is incredible. I'm even thinking about mapping, like when you think about how to create like a computer-generated three-dimensional topographical map. How do you think they tell the computer where to put the mountain and how tall it needs to be and how steep it needs to be? We're talking about Calc 3, really, right? But we're still talking about how do you take a crazy surface and describe it with numbers and variables and mathematical expressions. This is kind of the start of something like that. That's way more complicated, but we're trying to like build that out. So yeah, it can be, I think it's kind of interesting. Just because you can see it, touch it, you can visualize it pretty well. Gretchen, did you have a question?
Well, I'm just kind of wondering, is it possible to have like, I don't know how to describe this, but like a three-dimensional plane with like functions inside that three-dimensional
Yes.
frame that like you find the volume in those?
Yes.
Like there's one above it and one on the side of it and all around?
Yes. You're talking about Calc 3,
Okay.
but yes, you totally can. Yep, absolutely. You can have all kinds of different functions. You can find volumes under a surface. You can have these mountains going up and down, and you can say, what's the volume under this, or what's the surface area of all that? But it is Calc 3. You need like a third or fourth or fifth variable instead of just two. So, yeah, good question. I don't know. There's, obviously we can change the base region. Check this out. Here's the base region. And what if I change the lower function to just be, I don't know, maybe like a line, like x minus 1. See how it just changed? So let's see what that looks like. And then you could do equilateral triangles. This looks a little more like that Sydney Opera House thing, right? Ooh, it spins around too. Isosceles right triangles. So this is where one side is vertical on the little cross sections. And again, all we're really doing is instead of accumulating a bunch of washers or discs, we're accumulating these cross sections. And if I take my n back a ways from 40 to 12, you can see those cross sections a little more easily defined, right? You can see how it's kind of chunked out. You can see those triangles. It's a little harder to see with the region, although that kind of looks cool too if that were a building, I guess. Or you can ramp up the number of cross sections and say, it looked like this. There's 70. Now we're talking about something that looks almost perfectly smooth, at least on the screen, right? Okay. So from seeing it on a computer screen, is this starting to make sense? You see how Jake's idea of things will just sort of grow out at you is really what we're talking about? This is all just about visualization. We haven't talked about how to do it, because how to do it isn't that bad. It's just a visualization. I want to make sure that you understand how this is different from rotational solids. Any questions or just wonderments at this point? What ifs? Why this? What if we did that? Okay, so let's do this. Let's have one person from every table go grab some Play-Doh for their table. Sam, I hope you can handle it. All two of them. We'll do a little bit of Play-Dohing. Can do some Play-Dohing.
if you need something else.
What's
I
going
might
on?
be back by sometime
Okay.
this class.
Okay.
Yeah.
You know where to find us.
No, you don't. I get lost. Bob would get lost. All the people get lost in this thing.
And we'll go back and we'll talk about how we do this, and I'll give you some formulas. But again, we're kind of in the visualization stage right now. So what I want you to do is like think about number 6, try to picture what this would look like, make it with the Play-Doh. We can kind of mess around with that a little bit. We'll go back and we'll look at the formulas and how we actually find the volume, and then we'll try to find the volume of this. Does that make sense? We're still in the visualization part though, so try to make this. So this one says the cross sections are squares. So you got a circular base, and the cross sections are squares. And they could be triangles, they could be semicircular, they could be lots of stuff. Yep, for sure be named for you. See how this visualization went for you? So I've made this on the computer screen, just so we can see it a little bit easier. I can try to make it too, but sometimes mine is going to be probably more confusing than it is helpful. So you guys see the circular base, right? Here's what square cross sections look like. Can you see it? So these are what do you mean only one direction? No, because it's growing up out of the circle. Now, it's possible for us to word these questions in such a way that stuff might go below, but this one is worded in such a way that they're all above. So please notice a couple of things here. Let me go back. I guess it's just spinning. Let me go back a little ways on the n value. You guys see all the square cross sections? See them a little bit better? Yes? No? Okay. And then? Were you making little? Yes, that is the way to do it. I like what you were doing. So she made like a circular base, and then she started making little appropriately sized squares. That's a cool way to do it. I like it. So then as you increase the number of square cross sections, they get skinnier and the shape gets a little more smooth. And you can see, so like, Meg, do you see what I meant when I said it should be a little more broad on the top? Yours is a little more just like almost like a knife or something. It needs to be, yes, I think you're probably right. Anyways, and then let's do that. So if we had equilateral triangles, it would look like this, almost like a mohawk. You see that? Spiky hair, regular pentagons. That's kind of a cool looking shape. Semicircles. Not surprisingly, if you make semicircular cross sections on a circular base, what do you get? Not a semicircle, not a half circle, semi or hemisphere, right? Half of a sphere. Hemisphere, yeah. Anyways, but we're looking at squares, so that's what this is. Okay, so then the question is, you've got square cross sections, you got triangular cross sections, you got whatever you got. How do we find the volume of something like that? Let's do this. Let's figure this out. So go back to your notes and set your Play-Doh aside. Let's fill in a couple things here, and we'll actually fill this example out and figure out what it is. So go back to the start. Here are your formulas. If the cross sections are perpendicular to the x-axis, here's what it is. I hope that none of you are shocked that this is going to involve one of these guys, right? A whole bunch of really skinny squares, a whole bunch of really skinny rectangles or triangles. We need to add them up. The only way we can add something like that up is going to be with an integral. We're going to integrate from x equals a to x equals b, whatever those limits of accumulation would be. And then the integrand is super, super simple. I didn't say easy, I said simple. Here's what it is. A of x dx. So dx, of course, stands for the thickness. This time it's not going to be the thickness of a disc or the thickness of a washer. It's going to be the thickness of a little cross-sectional shape. Yeah, triangle, square, rectangle, whatever. And then a of x, anybody want to venture a guess as to what that might mean?
The formula for your shape.
Say again?
The formula for your shape.
What
Cross-section
formula for what?
for the area.
For the area, yes. So I'm going to put area of one of the cross sections. So if you took one of those squares, you took one of those rectangles or triangles or whatever it would be, we'd want to express the area for that. And then, of course, the good news is if the cross sections are perpendicular to the y-axis, it is exactly the same formula, except it's the integral from y equals c to y equals d of a of y dy. So it's the exact same concept, the exact same principle, just done in a different variable. What do you guys think? So what could the a of x be? Let's explore this briefly. What if the cross sections were triangles? What could a of x be?
1/2 y times x.
You're getting too specific. I'm just going to say 1/2 bh. And certainly in the b and the h, we're going to have some x's or y's or something, but just 1/2 bh. Just making sure you remember your formulas that would be key here. What if you had a square? What would be the most efficient way of expressing the area of a square? That is true, but it's not the most efficient way.
Length times height times.
Not- No, I would say what Dax said, like side squared. Is that okay? Like height squared, base squared. I usually tend to say whatever one of the side lengths is, squared. What if you had a rectangular cross section? Yep, that's going to be base times height. What if it was a lovely semicircle? That's supposed to be a semicircle. Yeah, 1/2 pi r squared. And I would say these would be the typical shapes we're looking at. Triangles, squares, rectangles, semicircles. It could be lots of other things. And it could even be some crazy shape whose area is defined for you in the question. I might say, hey, the area of each of these cross sections is, and gives you some formula that you would have had no way of knowing, but they just told it to you, right? So there could be some other options there. But as far as just the standard geometry formulas you need to remember, these would be it. So if you look at that list and you think, yeah, all 4 of those, I got those, no problem, I think we're good. But if you look at them and you're like, oh man, I always forget the area formula for a circle, might be something you want to review a little bit, because it would be expected that you would know that. Fair enough? Okay. So let's go back to number 6. Let's go back to that one, and let's see if we can figure out what the volume is right here. Number 6. Okay, it says, find the volume of the solid formed with cross sections perpendicular to the y-axis that are squares. Circular base, x squared plus y squared equals 9. And so what I'm going to do is sketch out the base. I'm not going to get too hung up on trying to draw this shape out. Some of these are pretty tough to draw out. I will do my best with this. So here is a perspective drawing. Hopefully a decent one. See, that's a circle in perspective. It's a little flat on one side, but does that make sense? Okay. So then I will draw in one cross section perpendicular to the y-axis. So and they're squares. Something like that. So again, this goes back to Jake's idea. What if they just like grew right out at you? I'm trying to make this grow right out at you, except it's kind of like up a little bit, right? Because of the perspective. Make sense? Okay, so once you recognize that it's volume created by cross sections, I really think you can do this. You can jump right away over here and say volume equals integral. And the first thing we need to do is we need to figure out, is this going to be a dy integrand or a dx? What do y'all think?
dx.
How thick? So we see the square there. We're trying to decide, like the dy dx decision is, what is the thickness measured on? Is it measured on an x scale or on a y scale? So it's binary, right? It's one or the other. You think it's x? Heard somebody say y?
Oh, wait. Perpendicular to the y-axis.
Perpendicular to the y-axis is what it says.
So that would mean it's y.
That would mean it's y. So he's changing. I like y too. I do. So here's y. I would say y. Let me three-dimensionalize this just a little bit. Right now there does not appear to be much thickness, right? Because I just drew like a line. But if I were to take this cross-section and give it a little more visual thickness, can you guys see how the thickness, and I'll do this in purple, do you see how the thickness right here is measured on the y-axis? Like the thickness is like a y-coordinate minus another y-coordinate. And so we would say that that cross-section is dy thick. And so what that means is I come over here to my integral and I say it's going to be integral of blah, blah, blah dy. Fair enough? Okay, second step. Let's figure out our limits of accumulation. Where do you think I would start accumulating these cross sections? For which y value? -3. Yep, I would start down here from y equals -3 to, where would I stop up there? It's also 3. Yep, so it'd be -3 to 3. And finally we get to the cross section. So the cross section's a square, right?
Yeah.
What's the area formula for a square? Side squared. So I could come in here and just put blank squared. That works. So then what I've boiled this down to now is, can I figure out how long the side of the square is? Let's be honest about this. Doesn't that sort of depend on something?
Yeah.
What does it depend on?
Where you are in the circle.
Yeah, where you are in the circle, like, yeah, as you look, left to right on the circle, is it going to be a really, really tiny square like on one of the ends? Or is it going to be a really large square like right smack in the middle, right? So it depends. It's going to change. And so what that means is this needs to be a variable expression, right? Because it's going to depend on wherever you are on the region. So let me illustrate this for you, and I think you can probably come up with this. I'll do this in blue. Would you guys agree with me that from here to here in blue, isn't that a visual representation of the side length of the square? What I just did in blue there? And you can see that depending on where you are in the region, that blue line is going to be shorter or longer, right? Just kind of depends on where you are. So we need to think of some variables. How could I describe the length of that blue line segment? It's not really diameter, though, because doesn't diameter have to go through the center? Now, one of them would be a diameter, for sure, but all the other ones would not. Do you guys know what those would be called? Chord. Nice. So impressed.
Geometry, sorry.
Yay. That's beautiful. Okay. So we got to think of the length of these chords, right? And they're going to vary. Anybody have any ideas? Anything jumping out to you?
Like 2x.
Oh, interesting. Why do you say 2x, Gretchen?
Because it's like the x value from the y-axis to the end of the circle, but it's also on the other side.
Yeah. You have discovered it. It's beautiful. Good work. So would you guys agree with me that from here, I'll do this in blue, from right here out to here, isn't that, if we want to be super literal, isn't that just an x?
Yes.
Like if you measure from the y-axis out to the right, I mean, we've just basically defined what x is on a graph at least. But then don't we have the exact same thing going on the left side?
Why can't you just all put it together as one x?
So, well, because x is defined as from the y-axis.
Okay.
So if I just put an x right there, I'm only measuring either to the right or to the left, but not both. So I need two of them, right? Because whatever the x-coordinate is, it'll get doubled, and that'll generate the length of the side of the square. Okay. So then that's all lovely and everything, but we can't leave it like that. What could I replace the x with? It's equivalent to it, but it only has y's in it.
Square root of 9 minus x.
Yeah, just take that circular equation.
Minus x.
No, you can't do that. Cannot do that. What you could do is this. You could, in place of the x, you could substitute square root 9 minus x squared. I'm getting that from here, right? I'm just solving for, it should be 9 minus y squared. I was getting ready to say it and realize that doesn't make any sense. Solve for x on that equation. And you get plus or minus. I'm only going to consider the plus, but because of the squared, doesn't really matter. Okay? So this would be one that you could probably do fairly easily without Math 9. But for now, let's just use Math 9. Let's figure out what this would be. Find this volume, and then we'll move on. I don't remember what this is. 44. 144. So exactly double. So, did one of you have the 2 in the squared and the other one not?
I did mine squared. I don't know if mine is.
But where was the 2? Was the 2 being squared also?
No.
The 2 should be squared. Like the whole side length should be squared. So technically, if you simplify this, it'd be 4 parentheses 9 minus y squared. Anybody else getting 144? 144, okay. So I think let's settle with that as our answer there, 144. Please don't worry about units. It'd be cubic whatevers, but since we weren't given units, we're not going to stress about that. Okay. Questions, concerns about anything like this? Can you see how the volume formula for a cylinder could come out of this? Pretty easily? You could get it by rotation too, but yeah. Okay, so if there's no questions, we're going to move on to number 7. Number 7. So number 7 looks like this. Find the volume of the solid formed with cross-sections perpendicular now to the x-axis. And the cross-sections are now rectangles, no longer squares. And the rectangles have a height of 3. The base is formed by that. Does anybody know what that is? Not a circle.
Oh.
An ellipse. Yes. Centered where? No. Centered at 0, 0. But the 5 and the 3 are also important numbers. Let's graph it.
That's the range.
Yay, there you go. There you go.
That's the
Let's this. So this is, I think getting the graph of this is probably a little outside the bounds of where we would typically go. So let's graph this together, and then I'll let you guys try to figure out what it looks like. Maybe set up the formula for the volume. So don't get too stressed if this gives you a little anxiety. Hopefully it doesn't. So it'd be x squared over 9 plus y squared over 25 is equal to 1, I think. Because remember, it's got to equal 1 to get into that standard form for an ellipse. So this is kind of a tall, skinny ellipse. So like 5 would be up there. Negative 5 would be there. Maybe that's 3 and 3. Something like that. Trying to make it look a little taller and skinnier than the circle did with the perspective. Okay, so please build some rectangular cross sections on that. Sketch it out real quick, just a very rudimentary sketch. Here is my cross section that's perpendicular to the x-axis. Maybe I'll put it right there. The height is 3. Something like that. Does that seem like a reasonable representation? I hope so. All right, so once you've realized that this is not discs because there's no rotation, once you've realized that it's not washers because, again, there's no rotation, nothing's being rotated around anything, There's no pies. There's nothing like that. I realize it's cross sections, so I'd write volume equals integral of blank, but then it's got to be either a dx or a dy. What do you think it is? It is a dx, right? Because we're perpendicular to the x. That's really where it comes from. So dx. So I'm going to be accumulating from left to right. So from on the far left edge all the way over to the far right edge. What are those x values that define those edges? 3 and -3. Yep. So be integrating from x equals -3 to x equals 3. And then I'm left simply with the area formula for a rectangle inside there. It's base times height. What's the one thing that we already know? Height is 3. So I could put 3 times base length. And what did you say, Addie?
2y.
You guys okay with the 2y concept like we just did with the circle? Okay. So it'd be 3 times 2y. Notice there's no squareds going on here because it's just base times height. Obviously with squares, it was side squared. So it's a little bit of a different formula. Okay, so then the last thing I've got to do is write down what y is, because I can't leave it like this. What is y equal to, or how do I get to it? Yeah, just take it up here and solve. So it'd be volume equals, check this out. What if I did this? 6 integral from -3 to 3. Make sense? Get the 2 and the 3 out of there. And then the y would just be, what, 2, would be the square root of 225 minus 25x squared over 9, right? dx. Technically plus or minus. I specifically chose the plus because I'm not about to square anything, so it would matter. If I chose the minus, I would obviously be getting a negative volume. Doesn't make that much sense. Jake? So the base length, doesn't the base length stretch from, I'll do this in purple, from here to here? That's a y, that's a y, so 2y? Okay. Anybody else?
I was wondering if the base wasn't like a nice ellipse. It was like a, I don't know, like a squiggly line on the bottom and a squiggly line on the top. But you had the function. Would you have to like first find the area of the function?
Can we do one just like what you're describing?
Yeah.
Not quite as squiggly as your finger did, but sort of close enough. Sorry, I didn't figure out what did anybody do the math 9 with that? 179? I don't know. People watching the video, you guys, if you want to really just math 9 that, go ahead. I'm way more concerned with the setup than I am getting to the actual answer. So Gretchen, this is kind of your thought right here. You said, what if it's not a circle? What if it's not a lovely ellipse or something like that? What if it's like some curvy thing and some other curvy thing? This, of course, is a curvy thing with a line. Same concept, though, right? So let's wrap it up with this one. And again, I want to take you through this. Hey guys, listen really quick. Can you tell from the words that there is no rotation? There's no washers. There's no disk. Because it doesn't say anything about the region R is rotated about or rotated around anything. It says the solid is created by cross sections perpendicular to the x-axis. So that means there are no r squareds, there are no pies, there are no washers, no disks, simply cross sections. So the cross sections, I'll sort of sketch these in, perpendicular to the x. So I'll try to perspectivize this a little bit. Does that make sense? Squares kind of, I've tried to make it jump out at you. Is that good? See the squares coming straight at you? If they really were coming straight at you, they would just look like line segments coming at you. Sort of? Yeah. Okay. So as soon as you see that it's cross sections, just go volume equals integral of something dy or something dx on this one. Have to be dx because we are perpendicular to the x. That's right. Okay, these are going to accumulate across this base region from where to where? 0 to 4, from left to right. Yep, because we're perpendicular to the x, we'll accumulate from 0 to 4. And the cross sections are what shape? What's the area formula for a square? So I'm going to do that, blank squared. And this finally gets around to Gretchen's question. If sorry, these aren't labeled. I should probably label these. This is from that earlier question. This is y equals root x. This is y equals x over 2. If I wanted to find that side length of the square, how do you think I would do it? Yeah, sorry. I assumed you remembered it from before, but that probably is, you got a lot going on. It's a little bit too big of an assumption on my part. So how do you think you could find, like even if I didn't give you those functions, what would you do? Subtraction, yes. Isn't this length right here, the blue length, aren't all those simply high minus low? So in here I would write, x said it first, square root of x minus x over 2. They're all in terms of x, so I think we're good. Technically, this would be like y2 minus y1, but I'm going to transition to a point at some point where I'm just going to like automatically substitute those, but
There's no 2 times anything?
nope.
Oh,
There's
so
not, because simply we're just looking for how long is that blue line,
Yeah.
and all it really is curve minus line. That'll give us the length of that blue line. So I hope I give you a lot of good, like different varying experiences today with like circles and ellipses, and then this. So then on Tuesday of next week, we have one left over, and it's going to be triangle cross sections, if I remember correctly. That'll maybe be a good way to connect the 2 weeks together and give us momentum for next week. So have a wonderful rest of your day. Just leave the Play-Doh out, and I'll look forward to seeing you guys next week, next Tuesday.